Hey everyone, my name is Taylor Sparks. I'm the editor-in-chief of Integrating Materials and Manufacturing Innovation. And today's paper, I'd like to talk about acoustic emission depth analysis for plate-like structures. This work comes to us from the University of California, Santa Barbara, from NASA Glenn Research Center, from the University of Michigan, and Air Force Research Lab. Lead author here is Tulshibagwale. All right, let's dive right into it. Okay, so ultrasound or acoustic emissions have become a really popular way to characterize composite structures. You can look at damage that occurs and not just know that damage occurs, but you would like to be able to assess how deep that damage occurred within the material. Was it near the surface? Was it in the middle? Was it on the back end? And that's a challenge. And that's specifically what this paper is going to try and tackle. They're going to take acoustic emission signals and they're going to try and identify whether that occurred from the top or the bottom of the plate. The catch is, though, that in traditional approaches, the sources occurring on opposite sides of a plate generate nearly identical waveforms. And so traditional acoustic emission features like peak frequency or amplitude, they just don't serve as good, sort of reliable ways to distinguish whether the damage occurred from the top or the bottom. So to do their analysis, here's what the authors did. They're going to actually set up a series of experiments doing pencil lead breaks, literally mechanical pencil, snapping on this aluminum surface. They're going to break it a bunch of different times, like they did this on the top, the side, the bottom of the aluminum plate, and they recorded over 1,600 waveforms under varying sensor coupling and source distance conditions. So they've got a ton of data of actual waveforms breaking on the top and bottom and in the middle. So what are they going to do with that then? Okay, what they're going to do, and I think what's sort of the central figure of this paper, is they're going to analyze the features that different models use when making the classification top, bottom, or side. The authors compared a bunch of different models, right? They did all logistic regression, support vector machines, random forest, neural networks, CNNs, a bunch of different things. But what was surprising, at least to me, is that the model didn't make that big of a difference. What really made a big difference was the features and the dimensionality of the features. A common approach here is when you take this acoustic emission waveform, is there's a bit of feature reduction, right? So you squeeze it down to a lower dimensional feature, and these did not perform very well. You have a hard time determining source to sensor distances in that approach. In contrast, when you give it a more higher dimensional feature, giving it more of the information basically, for example, the 26-dimensional partial power representation of the frequency, this achieved the highest classification accuracy, almost 90%, on previously unseen source distances. So far, far better. Why is that? This figure, I think, helps explain why. If you look at, this is plotting some very simple features that are commonly extracted, like, for example, the frequency centroid plotted against the maximum amplitude. What you see is that, take a look at emissions from the top versus the bottom, the blue and the green. They're basically overlapping, right? So whatever your choice of algorithm is, it's going to have a very hard time separating out this data because it is overlapping so much. We're simply losing information that's necessary to make the correct classification in these low dimensional representations. On the other hand, when you give it the full spectrum, right, this is where it gets, I think, kind of interesting. There's subtle information captured here. And in this plot, what you're seeing is amplitude is a function of time, right, for these different sort of waveforms. And what you're seeing overlaid on top of that is it's an analysis that shows you, it's called a saliency map. And it's showing you where the convolutional neural network is paying attention. In other words, what parts of this waveform were really important for making the analysis, the classification decision that it made. When I look at this, what I basically see is that the models seem to be focusing strongly or paying more attention to this initial arriving portion of the waveform. That very first part that hits the sensor seems to be important. And to me, that makes physical sense, right? Because when it first arrives at the waveform, that must be the source-related information, because the stuff that comes later includes information from the reflection, which is just going to complicate the signal. So it's no wonder that it's paying close attention to that, which I think pretty slick. And the authors also show that this, even though raw waveform models do tend to overfit, a CNN can actually learn physically meaningful features related to the waveform polarity, modal content, and dispersion, which is pretty slick. So what's the takeaway here? The big takeaway for the paper is that acoustic emission signals contain enough information to classify which side the event originated from, even when the traditional approaches of doing feature reduction would fail. Rather than replacing sort of them with these physics-based inversion methods, the authors now propose just simply using machine learning as a pre-processing step to constrain your solution space and make future depth reconstruction all that much more practical. A cool example of where better engineering, and not necessarily with deeper neural networks, but with better understanding of the feature engineering space, gives you the greatest performance gains. I hope you'll read all about it in the latest issue of IMMI.